Okay, so in the last lecture we had discussed about the concept behind limits of multivariable functions, right? Okay, so in this particular lecture we are going to start with the concept to check when a limit does not exist. So let us just recall a few things. That is, when we had single variable function, let's let y equals to fx, and suppose we have a limit when x approaches a, if x approaches a. Now, when can we say that this limit does not exist? Okay, so remember, we used to do something like this, that if limit x tends to a plus fx does not equal limit x tends to a minus fx, we used to say that the limit of the function does not exist, right? So what does this basically meant? So this basically meant that when we approach this point a from the left side, we get this limit, and when we approach a from the right side, we get this limit. Okay, and when approaching from both these directions, the value of the limit, or the value which fx tends to reach, is not same. We used to say that the limit x tends to a fx does not exist, right? So we can clearly see that for some limit to exist, we need to check whether approaching that point from every possible direction gives you the same value for the function, right? So we have a similar concept here as well. So if from the two different paths as xy approaches to x0, y0, the function fxy has different limits, that is fxy tends to different values, then we say that this limit does not exist. Okay, what I mean by this statement is that suppose you have a function fxy, okay, and you take this point x0, y0. Okay, you take this point x0, y0. So this is the region around x0, y0, right? So for x y to approach x0, y0, we can take several paths. We can take several paths. Okay, suppose you have xy here, let's say. So xy can take several paths. It can come straight to x0, y0. It can follow a path like this. It can follow a path like this. It can follow a path like this. Approaching x0, y0 from each of these, there can be infinitely many paths, right? So approaching x0, y0 from infinitely many paths, if the value, if fxy tends to the same value, then only we can say that the limit exists, else not, right? So the main concept behind this is that the value of this particular limit must be path independent, right? We can take any path to reach this point x0, y0, and still the function fxy must approach the same value. So let us check. So suppose we are given this question that as xy approaches origin, what is the value of the limit x square plus y square? Okay, let's check. Suppose we try to approach x0, y0 along the x-axis. Okay, so this is your origin, right? Now suppose we tend to approach towards 0 comma 0 along the x-axis. Along the x-axis means we have y equals to 0, obviously, right? Suppose we take a point here which is x0, and we tend to reach, we try to reach 0 0 along x-axis. Okay, clear? Okay, now if we take a point on the x-axis, then limit xy tends to 0 comma 0 automatically gets changed to limit x tends to 0, because y is already 0 here, right? So we can basically convert this limit to limit x tends to 0 where y is equals to 0 of the given function, and we can obviously see that the value of this function is 0, right? Because if you put 0 in place of x, you get the value as 0. Okay, we cannot put y here obviously because you are given a multivariable function. Being y is equals to 0 does not, you have y equals to 0 here, but you cannot put that here because y equals to 0 is basically the point which we are trying to approach 0 comma 0. Got it? Okay, so as y is fixed to be 0, we just have a point with an abscissa which tries to reach 0 comma 0, and when we do so, this becomes a function where only one of the variables is trying to approach a given point, the other one is fixed. Got it? So in this case, we get the value of the function to be 0. Similarly, if we try to reach 0, 0 with a point on the y-axis, okay, with a point on the y-axis, here your x is fixed to be 0. Every point along this direction has x equals to 0. So the limit only y tends to 0 remains, and still the value of the function comes out to be 0. Got it? So it seems that the function might exist, but there are infinitely many more paths along which any point xy can reach 0, 0, because see, xy is given to be an arbitrary point. Are you getting it? Xy is given to be an arbitrary point. It can be any point on the xy plane. It can be a point on the y-axis, it can be a point on the x-axis, it can be a point on the xy plane, not being any point on the x-axis or y-axis, right? If it is not being on the x or y axis, it can be any point on the plane. Thus, we have x not equals to 0 and y not equals to 0. And the point is approaching the origin, right? So, suppose this is the origin, obviously, and you take a point somewhere, let's say here. You take the point such that this point lies on the curve y equals to x. Clear? Got it. Now, if this point is on the curve y equals to x, then we can obviously say that along y equals to x tends to 0 implies y tends to 0. Okay, x tends to 0 implies y tends to 0. Or we can do one more thing. Okay, let us check it like this. Yeah. Okay. So along y equals to x. Along y equals to x. Along y equals to x, what we will do is that, so see, as I was telling, the limit xy tends to 0 can be changed to limit x tends to 0. And since you have y equals to x along every point in this path, you can obviously put x equals to y in the given function. So it changes to x square over 2x square, and limit x tends to 0, x square over 2x square seems like a single variable function which gives you the value 1 over 2. But 1 over 2 is not same as 0. So as we change our path to approach the origin, the value of the limit of the function changes. Therefore, we can obviously say that this limit does not exist. Is it clear? Let us check one more problem. Okay, suppose this one. Okay, you have limit xy tends to 0, 0, x cube y over x to the power 6 plus y square, and you need to check whether this limit exists or not. Now see, we can do one more thing to check whether this limit exists or not. See carefully. So since xy is any arbitrary point, we can take, suppose you have y is equals to mx cube. Okay, you can take a curve y is equals to mx cube, and we can say that xy is a point on this curve and it is approaching 0, 0 along the path of this particular curve. Now, how can we choose the path? See, the path must be such that origin falls in this particular path. Otherwise, the point won't be able to approach the origin, right? Now 0, 0 is obviously a point in this path. Therefore, we can take xy as an arbitrary point of this particular path which seems to reach or approach for the origin. Now, if you take y is equals to mx cube, we can obviously see here that limit y tends to 0, sorry, limit xy tends to 0, 0 can be changed to limit x tends to 0. Okay, because x tends to 0, see, automatically implies that y tends to 0. Is it clear? And since we have taken y is equals to mx cube, we can put y equals to mx cube in the function. So you get x cube times m times x cube divided by x to the power 6 plus m square x to the power 6. Is it clear? This can be written as limit x tends to 0. Now you have here m x to the power 6, and from the denominator you can take x to the power 6 common. You have 1 plus m square left. Okay, now this cancel out. since x is not equals to 0. So you're left with m over 1 plus m square, which seems to be a constant, right? Because we have taken m as an arbitrary constant as the slope of this, not slope, m as an arbitrary constant of this particular curve. Okay. So you're left with this particular value. Now see, as m changes, the path changes. This particular path changes as m changes. And we can see that this particular limit is depending upon the path of this path which the arbitrary point xy takes to reach the origin, right? Therefore, we can say that this limit is path dependent. And we have already seen that the limit if becomes path dependent does not exist, because since this limit is path dependent, as we change the path, the value of the limit will obviously change, right? So that basically implies that this function does that this limit does not exist. Okay, we have one more example here which is kind of same as the above two examples. Here you have three variables. Okay, x, y, z. All the three approach to 0. That is, x, y, z approaches origin in the 3D plane, and we have this particular function. Now here, if you take x as kt square, y equals to t, and z equals to t, then as x tends to 0, y tends to 0, and z tends to 0, t tends to 0 as well, right? And the function changes to putting x equals to kt square, y equals to t, and z equals to t in the given function. You can change the function to kt to the power 4 over k square t to the power 4 plus 2t to the power 4. T to the power 4 comes out and cancels because t is not equals to 0, and the value of the limit comes out to be k over k square plus 2. Thus this particular limit also becomes path dependent, hence does not exist. Is it clear? Is this particular concept clear? Okay. Next, let us check what is the concept of double limits and iterated limits. Okay. So the limits which we were calculating right now, that we have a point xy on the xy plane, which tends to or approaches to some point x0 y0. Then the function fxy tends to the value L. So we say limit xy tends to x0 y0 fxy equals to L. Now suppose we don't kind of try to tend the point xy towards x0 y0 for the function fxy, but what we do is that we try to approach a point, or we try to reach a point first by the ordinate, then by the abscissa, or first by the abscissa, then by the ordinate. What I'm trying to say is that suppose you have a point here xy, okay, and you need to reach the origin. Okay, you need to reach the origin. That is, xy tries to reach the origin. So what you can do is that you can first come directly to the origin, not mandatory that it must take this path only. You can come like this, or you can come like this. But what I'm trying to say is that this point directly reaches origin, okay, which gives you the, or which is calculated in case of the double limit. But what more we can do? Suppose I first make this point reach the y-axis. So approaching y-axis means we are tending x towards 0, and then from along the y-axis we try to reach the origin, that is y tends to 0. Is it clear? Or what we can do is that we can first make the point reach the x-axis, that is y tends to 0, which is y tends to 0, and next we try to make this point reach the origin, that is x tends to 0. So what we are basically doing is that we are dividing this particular limit, this particular path of xy approaching the origin, to x tends to 0 after y tends to 0, or y tends to 0 after x tends to 0. This gives you the concept of iterated limit. So what is iterated limit? fxy, where iterated limit of fxy is basically first letting y approach y0 and then x approaching x0, or first letting x approach x0 and then y approach y0. So in these two cases also we are making xy reach x0 y0, but taking paths independently. Clear? Okay. I hope this particular concept is clear. Right. Now see, if double limit of xy tends to x0 y0 fxy equals to L, that is if the double limit of fxy as xy tends to x0 y0 is L, Then the iterated limits where fxy tries to approach something first when y approaches y0 and then x approaches x0 is same as the value towards which fxy tends first as x tends to x0 then y tends to y0 and both the values comes out to be L. What is the reason behind it? See, I already said that as xy tending to x0 y0 here, xy is also tending to x0 y0 here as well. But just what we are doing is that we are taking a different path. Okay, here we are taking a different path. We are trying to approach x0 y0 directly along any path, and here what we are doing is that we are first trying to make the ordinate reach y0 and then the abscissa reach x0 or the reverse, right? But since the limit of a function is path independent, so we can take any random path and still reach the value L. Therefore, if this double limit exists, the value of the iterated limits must also be L. Is it clear? But when is it true? This is true only if this limit or this limit exists. Because if these two limits does not exist, then we cannot say that the iterated limits must satisfy this particular condition. Because for the iterated limits to exist, these limits must exist. Is it clear? But the reverse of this implication need not be true. The converse of this particular statement need not be true. Let's see. Let's see. So here we have taken a double limit. Xy tends to the origin, x plus y over x minus y, and x minus y is given not equal to 0. So its iterated limit seems something like this: y tends to 0 and then x tends to 0 of this function. Now as y tends to 0, this becomes x over x, right? And x over x cancels out because x is not equal to 0 till now. So it gives you the value 1. Okay, you can calculate it on your own. Limit x tends to 0, limit y tends to 0, x plus y over x minus y equals limit x tends to 0, x over x, which cancels out since x is not equals to 0, which is equals to 1. The same thing if you do by first making x approach 0 and then y approach 0, then you get minus 1. Okay, hence these two iterated limits exist, but they're not same. And as they're not same, we can obviously say that the value of this particular function as xy tends to 0 comma 0 is not same if we take two different paths. Hence the limit must not exist. Is it clear? So the double limit does not exist, but its iterated limits do exist. Is it clear? Got it? Okay. Let's check some more examples. Suppose you have this function given. Okay, you can check it on your own. So in this case, if you take the iterated limits into consideration, you will get the value 0 and 0, and both the values are same. X tends to 0 of limit y tends to 0 fxy is same as limit y tends to 0 as limit x tends to 0 of fxy. Okay, clear? They are same and they are equals to 0, but still the limit of the function does not exist. Why? Because if you come along the path y equals to x, then this limit gives the value 1. Okay, therefore it becomes different for different paths, hence the value of the limit does not exist. Is it clear? Is it completely clear? Got it? Okay. Next, let us check what is the concept of continuity of a multivariable function. Okay, so a function fxy is continuous at the point x0 y0 if f is defined at x0 y0, limit the double limit xy tending to x0 y0 of fxy exists, and the double limit fxy tending to x0 y0 of fxy must be equals to the value of the function at the point towards which the xy is approaching. Is it clear? Seems relatable to what we have studied in single variable functions, right? Now, when is a function is said to be continuous in a given interval? So, function is continuous if it is continuous at every point of its domain. Then we can say in its complete domain the function is completely continuous. Okay, continuity at a point and continuity in an interval obviously differs. continuity of a point and continuity in an interval obviously differs. A function is said to be continuous. I have missed some statement here. A function is said to be completely continuous if it is continuous at every point of its domain. Clear? Okay. Now suppose we are given these two examples. Okay, let's check. Let's check. So the first particular example, limit xy tending to 0 comma we are asked whether this function at 0 at the origin is continuous or not. Now see, this function, as we approach this particular function, I mean as we approach this particular function, sorry, as we approach the point of as we approach origin along this particular path y equals to mx, then the value of this particular limit becomes path dependent because it becomes dependent on m, right? As the value of the limit does not exist. If this value of the limit does not exist, then we can obviously say that this function is discontinuous at the origin. Is it clear? It is very simple to understand. Is it clear? Let us check the next one. So this particular function, in this case also same thing happens. So if you reach, if you try to reach the point origin along y equals to 0, that is along the x-axis, you get the value of the limit as 1. And if you try to reach this function along the path y equals to x square, you get the value as half. Okay, so two different paths gives you two different value of the limits, hence the function is not continuous at the origin. Is it clear? Is it clear? Now you are given this particular function. fxy is 2x times x square minus y square over x square plus y square, as xy is not equals to 0 and 0 when xy equals to 0. Is it clear? So what are you asked to find out? You are asked to find out whether this function is continuous at origin or not. Okay, let's see. So firstly, see, does this function exist at the point of origin? Yes, because the function is giving the value 0 at origin. It is defined. Therefore, f exists at origin. Okay. Now, will the value of this limit exist? Let us check that. So we can check that using the delta epsilon proof in this case. Okay. So to check the delta epsilon proof, what we can do is that we can first do some scratch work, that is some back calculation of the actual delta epsilon definition to get the value of delta related to epsilon. Okay. So if we take 2x times x square minus y square over x square plus y square, because we basically need to check what we basically need to check whether the value of this limit as xy tends to 0 comma 0 is 0 or not. Okay, so we can basically check using delta epsilon proof, delta epsilon definition, what is the value of the limit of this particular function. If it comes out to be 0, then okay. So suppose mod of this is less than epsilon. Okay, so from here we can say 2x cube over x square plus y square minus 2xy square over x square plus y square, and the modulus of this is less than epsilon. Is less than epsilon. Now we know mod of a minus b is obviously less than equals to mod a plus mod b. Okay, so since we are doing the back calculation, we can replace this particular value with this, right? That is the same thing which we have done here. So we have replaced this with mod of 2x cube over x square plus y square plus mod of 2xy square over x square plus y square, and the value of this is less than epsilon. Okay, now what we can do? Now we can take x square 2 mod x common from here, let's say. That is what we are doing is that, see, so this can be done as 2x times x square over x square plus y square plus 2x times y square over x square plus y square, and this is less than epsilon. Now we know mod of ab is equals to mod a times mod b, so we can write it like mod of 2 is 2 itself, so mod 2 mod x mod of x square over x square plus y square plus 2 mod x mod of y square over x square plus y square is less than epsilon. Now this is less than 1 and this is less than 1, right? So we can change this to 2 mod x plus 2 mod x less than epsilon. which gives you 4 mod x is less than epsilon. And since mod x must be less than delta, since mod x must be less than delta, so 4 mod x must be less than 4 delta. So what we can do is that we can take 4 delta less than epsilon, that is delta less than epsilon over 4, and then we can go on with our delta epsilon definition. So let's see. I hope you people have understood what is the back calculation. Okay, now see. So if we take delta is less than epsilon over, so what we can do is that, so for all epsilon greater than 0, there exists delta greater than 0 such that delta is less than epsilon over 4. Now mod x, mod of x minus 0 less than delta implies mod of x is less than delta, which implies 4 times mod of x is less than 4 delta. Now 4 times mod of x is 2 times mod of x plus 2 times mod of x, which is less than 4 delta. Now we can write this as 2 times mod of x times mod of x square over x square plus y square plus 2 mod of x times mod of y square over x square plus y square, and it is less than 4 delta. The reason is that mod of x square over x square plus y square is less than equals to 1, and y square over x square plus y square, its modulus is also less than equals to 1. Okay, clear? Now then what we can do here is that, so we can now write it like 2 times, sorry, modulus of 2x cube over x square plus y square plus modulus of 2xy square over x square plus y square is less than 4 delta. Now mod of a minus b is less than mod a plus mod b. In this case, if you take this as a and this as b, so mod a plus mod b is less than 4 delta, so we can replace this particular value with mod of a minus b. So we can write it like this: 2x cube over x square plus y square minus 2xy square over x cube plus y square is less than 4 delta. So from here you can take 2x common, right? So what was the function given? Yeah, so if you take 2x common from here, so you get 2x times x square minus y square over x square plus y square is less than 4 delta. Since delta was less than epsilon by 4, so this is less than epsilon. So by the delta epsilon definition, we can say limit xy tends to origin 2x times x square minus y square over x square plus y square equals to 0. So from here what we can conclude? So from here we can conclude that f of xy as limit xy tends to 0 0 exists and equals f at 0 comma 0, because it is already defined that f at 0 comma 0 is 0. Okay, therefore the function is continuous at origin. Is it clear? Is it clear? Okay, so you can check the existence of this particular limit as well. Okay. You can do it on your own. A simple hint is mod of sine of 1 over x is less than 1. You can use this. Okay, this is a very important example. If you know try to find out whether this particular function y of sine of 1 over x, this particular limit exists or not, you will see that this limit will exist at 0 over 0 when the function is defined as f at 0 comma 0 is 0. Okay, you will see. I think the function is defined like, yeah, got it, as at x equals to 0, the value of the function is 0 when you're given this. Okay, but at x equals to 0, value of the function is 0, and you make xy approach origin, you get this. Okay, but you will see that one of the iterated limits does not exist. One of the iterated limit does not exist. Okay, because this particular limit won't exist. Limit x tends to 0, sine of 1 over x does not exist. Is it clear? Got it? Now we come to the concept of partial derivatives. What is the concept of partial derivatives? Now, in case of single variable function, we already knew the concept of derivatives, right? So, suppose we write this ddx of fx at x equals to a, which is also written as f dash a, which was also written as dy over dx at x equals to a, where y was the function fx. This was given as the limit h tends to 0, f of a plus h minus f of a over h. Okay, this was what we call the derivative of a function which has only one variable or one independent function, one independent value. In case we have more than one independent value, what happens is that, see, for example, we have this multivariable function z equals to fxy. Now the value of this function might change along the x-axis or along the y-axis. What I mean by this statement is that the value of this function might change along the abscissa or along the ordinate. Now when we try to change the value of this function along the abscissa, then we will get the derivative of this particular function or the rate of change of this function along that particular axis only. Or if we try to kind of find the change of this particular function along the axis of the other variable, we will get the rate of change along that particular axis of that particular variable only. So in this case, since we need to find the rate of change of this function along different axes due to because it has different independent variables, that is the reason why we call the derivative of this function with respect to given variable as partial derivatives, right? Because here we need to find the derivatives partially with respect to only one of the given independent variables at a time. Okay, for example, del f over del x at some point ab gives you the rate of change of this function along the change of the x variable only. In this case, the y variable is constant for this particular function, or the rate of change of this function is taking place along the x axis only. Any change in the y axis is not taking place. Is it clear? So we can write this particular thing as limit h tends to 0, f of a plus h, because the abscissa is changing only. So f of a plus h comma b, because b stays, because we need to find the derivative of this particular function at this point, at this given point. At this given point, only the abscissa is changing, but the ordinate is fixed to be b. So f of a plus h b minus f of ab over h. This gives you the value of the derivative of the function with respect to the variable x. And a similar definition will give you the value of the derivative of the function at the point ab with respect to the variable y as limit h tends to 0, f of a comma b plus h minus f of ab over h. Is it clear? Is it clear? Is it clear? See, here is also one more significance of this partial derivative given. So del f over del x at ab basically means finding the slope of the tangent for the function z at for the function f of x b, where y equals to b is kept constant. Okay, in the given line y equals to b, where x is only changing at the point a b f of ab, right? And in this particular point, the slope of the tangent of this particular function f of xb along the path y equals to b, because along the path y equals to b, y is constant, the value of y is fixed to be b. Is it clear? Got it? Now a simple sense of finding partial derivative is that if you are given to find the partial derivative of some function with respect to x, then throughout the process just treat y as a constant or any variable except x as a constant, unless that particular variable is a dependent variable. Any independent variable, see, if you are given a function z is equals to f of x1 x2 x3 xn, del f over del x. We can find this particular value del f over del x by differentiating z simply with respect to x, as we used to do in case of, sorry, del f over del x1, let's say, because you have n independent variables here. So del f over del x1, basically, as we used to find derivatives in case of single variable function, we will do the same process here. Find the derivative of this particular function with respect to x1, treating every other independent variable as constants, nothing else. Clear? For example, if you're asked, if you're given this particular function, f of xy equals to 3x cube plus 4x square y minus 6y square, what is the value of del f over del x? Now, differentiation of 3x cube with respect to x is 3 times 3 x to the power 3 minus 2 square, right? Plus, now y is treated as a constant because we are finding the differentiation of this value with respect to x. So y is just a constant, so this gives you 4y, and the derivative of x square is 2x, right? Minus differentiation of y will be 0 because y is treated as a constant, is 0. So this comes out to be 9x square plus 8xy. In exactly similar way, you can find del f over del y, right? Del f over del y will be, so differentiation of 3x cube will be 0 because x is a constant in this case. Okay, y is treated as a constant in this case, and x is treated as a constant in this case. Okay, so del f over del y will give you, so this particular value, oh, here you have y square. I have taken y here. This is y square. Okay, so here what happens? So 4x square times derivative of y square, it is 2y, so 8y square minus this is 18y square, right? Now one more notation, just know this, that del f over del x can be written as fx, and del f over del y is written as f. Got it? Okay. Now there is one more example here, f of tan inverse y over x. You can try it on your own. These are the given answers. Okay. Now there are some more examples here. These are done. Okay, these are the examples just we did here. Okay. Okay, here is one more. Find del z over del x and del z over del y if the equation x square plus y square plus z square plus 6xyz equals to 1 defines z as a function of two independent variables x and y. Okay, this is a good question. See, let us recall one more thing. When we used to have single variable function, let's say y is equals to fx. Let us take an example of the of somewhat similar. Let's say, so you have the function x square plus y square plus 6xy equals to 1, and you need to find dy over dx. What we used to do? We used to differentiate this particular equation with respect to x. So x square differentiation with respect to x is 2x. What we used to do in the case of 2y? What we should do is that we used to differentiate y square, or differentiate whatever y term we have got, same as we would have done if we had been given differentiation with respect to y. So y square differentiation with respect to y will give you 2y, and we multiply this with dy over dx. Remember? Plus this becomes product rule, right? So 6x times differentiation of y with respect to x is dy over dx, plus 6y times differentiation of x is 1 equals to 0. From here you take dy over dx common. So you have 2y plus 6x equals to minus of 2x plus 6y, right? So from here you get dy over dx equals to minus 2x plus 6y divided by 2y plus 6x. This was the method. Now why we can do it is that, so you have a y term. You have a y term. Basically, y square is a function of y, right? So we can write that d of fy over dy, that is differentiating the function of y or whatever y term we have got with respect to y, times dy over dx. This is same as ddx of fy. So this is the thing which we were trying to do, right? The same method we will be doing here. Okay, see. So to find del z over del x, what we do is that we differentiate this particular equation partially with respect to x. So when we are differentiating this particular equation partially with respect to x, we are treating every independent variable except x to be constant. The only independent variable except x present here is y. So we are treating y to be constant, right? So differentiation of x square with respect to x is 2x. Differentiation of y square with respect to y is 0 because y is a constant. Differentiation of z square with respect to x is same as we were doing here. Okay. So z square differentiating as similarly as we would have done in case of differentiating this with respect to z is 2z times del z over del x. Okay. So 2z times del z over del x plus 6yz, product rule, right? Taking yz and 6 outside and differentiating x. Differentiation of x is 1, and then we take xy outside, and because y is constant, so y will be outside in both these cases, right? So differentiation of z is del z over del x, right? This equals 0. We take del z over del x common, we get 2z plus 6xy equals to minus 2x plus 6yz, and we get del z over del x equals to minus 2x plus 6yz over 2z plus 6xy. Is it clear? In the exact similar way, we can find the value of del z over del y. Here in this case, x will be treated as a constant. Clear? Clear? Okay, so we are given some more functions here. So I request you people to find the values of del f over del x, del f over del y, and del f over del z in these three problems. In these three problems, you can see that we have three independent variables. X, Y, Z all are independent variables. Okay. You can do these problems on your own. So let this lecture be up to this much, guys. In the next lecture, we will be talking about some more concepts related to multivariable calculus. Okay. So we do, guys, in the next lecture.